Department at National Taiwan University of Science and Technology. Today he's going to share some fascinating insights on hydrogen storage. Now Professor Huang is the director of the ATW Solid State Hydrogen Energy Research Center, and he has an impressive track record. He has published a lot of researches, hold several patents, and also he's known for his dynamic partnerships with the industry. So today our seminar's title is From Lab to Industry Economic Breakthroughs in Hydrogen Storage from Mechanical-Based Metal Hydride. So let's give a warm welcome to Professor Huang as he takes this stage.
Okay, thank you for introduction. I'm Isaac Huang from Taiwan. It's my probably third time or fourth time in New Zealand. So I think in the green island, green country, the green energy is also important. In Taiwan, we study a lot the green energy, especially the hydrogen storage in our countries. So today my topic will be the from lab to industry, economic breakthroughs in hydrogen storage from magnesium-based metal hydride. Actually, the ATW Solid State Hydrogen Energy Research Center just founded 2 years ago. 2 years ago, and I studied this topic almost 10 years in the hydrogen storage. I'm so lucky to be ranked top 2 scientists in 2023 and 2024. Also, I have more than 20 years experience in magnesium composite material study. And then about 12 years ago, I do my research as a visiting professor in Weizmann Institute of Science, Israel. From that year, I started to more focus on magnesium hydrogen storage research. As you know, the energy for the future, from the statistic by the International Energy Agency, the world consume oil 105 million barrels per day, in coal 22 million tons per day, so huge. And the problem is that the pollution, emission, and also harmful materials, the greenhouse gases, accompany with the global warming. So now the fossil fuels are limited. So how can we find more new energy? And also there is the unstable price of the fossil fuels. And a lot of energy end up as a heat wasted to make the global warming. So during such a period of time, how can we find future energy? And as you know, the sustainability development goal, the SDG 7 should be the affordable and clean energy. Not only a clean energy, but also affordable. Not very expensive. We can afford such a new clean energy. So such a goal ensure access to the affordable and reliable, sustainable, and modern energy. So hydrogen is one of the best choice. The hydrogen was that is clean energy storage, and so also decarbonization, yeah, from the hydrogen energy. Actually, from my PhD study research, I did a lot of metal matrix composite materials. Basically, nothing based on magnesium metal matrix composite. We can melt those. We can make the composite material by melt stirring technique. Also, we can make the extrusion of the magnesium alloy to make the tube for the back, joint, merida, joint. And then we also did some heat sink material from the magnesium metal matrix composite materials. It was about 20 years ago. I started this research, and then I studied in Russia, so we have a special processing technique that is ECAP, equal channel angular pressure, that can make the material more tough and more strength, from such a process, ECAP. And besides, we have studied the way of metal matrix composite materials, and we also can synthesize tungsten disulfide nanotube, which can enhance the property of metal matrix composite material from the tungsten disulfide nanotube. From such a research, we also filed some patents, and we have some licensing to the industrial companies. It was 12 years ago when I visited Israel, Weizmann Institute of Science. I started to thinking about how can I apply the magnesium metal matrix composite material to the storage, especially the hydrogen storage. And we also studied some micro oxidation, especially for the magnesium alloy. So why we have such a magnesium hydrogen storage? Because it's very interesting. Magnesium is lightweight, very light, and also resource rich, low cost. And more interesting is that it has the highest storage capacity, 7.6. It's the highest among all the elements, all the metal elements. But it has the disadvantage of high thermodynamic stability, and so also slow kinetics. So we need to overcome every disadvantage of such a materials. And why we use the hydrogen, magnesium as the hydrogen carrier, hydrogen storage. Actually, hydrogen is the simplest and most abundant element. As you know. So magnesium also abundant on the earth. Hydrogen also very abundant, element. So it's an energy carrier, not an energy source, but an energy carrier. We can deliver and store more energy. For example, in Taiwan we have a lot of wind we have a lot of solar energy, also wind energy, but we cannot keep the solar energy for a long time. We cannot save it. Yeah. But if we transfer such electricity to the produce hydrogen, and also we store the hydrogen can be stored for a long time, 1 week, 1 month, 1 year. And then when we want to use such energy, we can transfer the hydrogen to electricity. So hydrogen is very good energy carrier. Yeah. And hydrogen has very high energy density. You want to carry it, but you need to have very big density. Yeah. And also can be used in the fuel cell to generate electricity. And now in the market, there are about 10 million metric tons of hydrogen produced every year. Yeah. But it's not so big, but it's now it is increasing the hydrogen production. And in the storage, yeah, hydrogen from the hydrogen production, and then hydrogen carrier, and then we need to transport the hydrogen, and finally hydrogen application. Hydrogen carriers, there are many methods. For example, ammonias, or LOHC, methanol, and metal hydride. Metal hydride is the solid state storage method, and then we can transport such a hydrogen. Yeah. Hydrogen is very rich in the water. We can produce from water, but hydrogen production also electricity or energy consumptive. Yeah. But related to the energy density, you can see the coal is 25 to 35 megajoule per kilogram. Diesel 45, but hydrogen can have 150 megajoule per kilogram. So it's a lot. It has the largest, higher than the caloric value of combustion, more than others of fossil fuel. Yeah, and the water production is non-toxic water, and hydrogen is also easy to be recycled. Yeah. So, how can we store? What's the capacity of our storage? We can compare that. If we use the battery, 1 kilogram we can store just 0.5 kilowatt hour. But if the diesel, yeah, the energy density 13 kilowatt hour, hydrogen 40 kilowatt hour per kilogram. Yeah. And for our housing, every day probably we only use 10 to 15 kilowatt hour per day. But for a small store or company, probably we need 480. So at least we need to store 40 kilograms of hydrogen for about 500 kilowatt hour electricity. Yeah. But if we have good fuel cell, probably we can produce 1 megawatt, yeah, from 40 kilograms of hydrogen. Yeah. So actually, it's very huge electricity we can produce. Yeah. But in all the system of hydrogen technology, which part is very most costly? That is storage and transportation. Yeah. It costs about more than 50% of the cost of the hydrogen technology. Yeah. And use the hydrogen storage method. The traditional hydrogen storage first is compressed hydrogen, but we should compress it under high pressure, 350 or 700 bars. And second one is liquidized hydrogen, but the temperature should be very low, minus 250 degrees Celsius. Yeah. And also is energy consumptive. Yeah. So also very costly. Yeah, it's like a rocket. We want to launch rocket by the liquid hydrogen. And another category of the storage method is one is the chemical. Yeah, chemical. Yeah, chemical hydrogen carrier. One kind of chemical carrier that is liquid. Yeah. For example, ammonia as the hydrogen carrier, or liquid organic, hydrogen carrier, or methane, methanol as a hydrogen carrier, and solid hydrogen carriers, metal hydrides. Probably some of you know some of the hydrogen storage methods in your lab. And among all the chemical hydrogen carriers, we can know that the gravimetric content of ammonia is highest. It's about 17.6, and then methane, and then the methanol. And the energy, volumetric energy density, methanol has the largest, 15.5. And the carbon content, ammonia has 0 carbon content, but methanol and methane has large carbon content. So, most of them are emission free. They are non-emission free. All have emission. Okay. Ammonia as a hydrogen carrier. You can see we need to store the ammonia, and then we need to crack ammonia, and then also purify. A lot of process, but that can be merged to the ammonia transportation system in every country, many ports can use the ammonia as a hydrogen carrier. Methanol also can be used as a carrier, but we need the heating, cooling, and PSA process. And the most modern ones that is steam methane, steam methane reforming. Reforming is very more advanced process. But all of them are the liquid chemical storage. But how about the hydrogen and the solid metal hydride? Metal hydride carrier. We can compare the volumetric hydrogen capacity between compressed and cryogenic hydrogen, also metal hydride. You can see the volume capacity Metal hydride has 4 times or 5 times than the compressed gas. But a compressed gas has the problem of safety, also the cost of pressurization. The disadvantage. But cryogenic hydrogen has the huge thermal loss. And charge of the liquefaction. But metal hydride has a little drawbacks. Also, a big volume hydrogen capacity. And in our study, why we choose the magnesium as the metal hydride. First, there's no storage efficiency loss under 5,000 or 4,000 times of absorption desorption. And also the absorption desorption kinetics is faster from the magnesium alloy. And gravimetric capacity of synthesized materials, we can have above 6%. You know the USA Department of Energy has the 2025 target of the storage percentage, that is 5.5. And for the ultimate final target is 6.5. But now we can reach 6%, even 7% in laboratory. Laboratory is one case. In the industry is another case. In the laboratory, I can reach 6%. In industry, probably only 5.5. Okay, but there's the drawback from the magnesium metal hydride. First, the operation temperature is very high, 300 degrees Celsius or 375. And another drawback is the external heat source needed for the initial cycle to start. But we need to overcome those 2 drawbacks in order to industrialize in the company. So in our study, in our research, there are some parameters we need to study. That is first, gravimetric capacity. Second, thermodynamics. Third, reversibility. Fourth, the cycling. And what we need to overcome, that is operation temperature. Operation temperature. And the key factor that we need to study, that is microstructure of the material, and also modification and nano sizing and catalyst addition. And you can see the storage tank for the gaseorized, compressed, pressed gas tank. You have such big size, but in liquidized, smaller, and metallized, metal hydride, much smaller. But we can reach the largest capacity, that is 6.6. That is theoretical, percentage. But usually industry, we just can reach 5.5 or 6%. Yeah, for 4 kilograms of hydrogen, we can run 400 kilometers. It's similar to the electrical vehicle. Yeah. But if we can store 10 kilograms of hydrogen, it can run 1,000 kilometers. For example, today we went to mountain. We went to mountain, but we are shortage of the electricity. We were nervous about that because one day we just can run one charge, just 400 kilometers. But if we can use the bigger storage of the hydrogen, yeah, 1,000 kilometers should be okay for one charge. Yeah, in our study, what we put first is the alloy, magnesium alloy, AG31, 61, 91. Yeah, it's the typical engineering magnesium alloy, AG31, 61, 91, and which is much cheaper than the pure magnesium. So we use the cheaper and magnesium alloy. And what's the additives? Titanium, nickel, iron, palladium, and carbon black, CNT, graphene. And our capacity, we already reached 6%. That is, if we have the storage material 166 kilograms, we can store 10 kilograms of hydrogen. And then the car can run 1,000 kilometers. Yeah. So now our first goal in industry is that we can store 10 kilograms. 10 kilograms of hydrogen. Then the Mirai or Neso, Hyundai, they can run 1,000 kilometers. And how we make such a storage material? That is, first, we tested the material from the alloy. We put some additives, and then we sample them into the billet. And there's a special process that is ECAP. It's one kind of severe plastic deformation method, equal channel angular tracing. Also, we put the powder, the rest powder into the high energy ball milling machine to make the powder. And then we mix them together and then put into the hydrogen storage stack. Yeah. And the chemical reaction of the storage is very simple. Magnesium plus hydrogen from the magnesium hydride. But besides, there's one intermetallic material, or two. One is Mg17 aluminum 12. Another one is Mg2 Al aluminum 3. Yeah. There are two kind of intermetallic material formed in the alloy. And the working mechanism of such absorption, first is physical absorption. Second one, chemical absorption. One is physical absorption. Another one is chemical absorption. And in between, there's the surface penetration of the hydrogen. Also the diffusion. And hydride formation is very, very important. During the processing, hydride formed. Yeah. And after we dissolve the hydrogen, the metal transfer back to, the hydrogen transform to the metal and the hydrogen. So that is our, we studied research result. Yeah. We have many kinds of additives. For example, nickels. Yeah. If we use nickels and magnesium alloy, AZ31, we can reach highest capacity, that is 7%. I think now in the academia, that is the highest capacity of storage, 7%. But the kinetic is not so quick. Yeah, it takes 40 minutes to absorb the hydrogen. Yeah, if we use the carbonate material, for example, carbon black, graphene, yeah, the kinetic can be quicker. Yeah, probably only 20 minutes we can absorb. Yeah. But the capacity decreased a little bit, but it's still high, 6.8 or 6.7. And recently we studied palladium material and with the multi-wall CNT, MW CNT, and the kinetics become very quick. Yeah, about 15 minutes or 9 minutes we can absorb, and dissolvation. Yeah, about 10 minutes or just 6 minutes can dissolve. And the capacity is about 7.1, 7.15. It's still quite high, but kinetics improved. But how we can implement such a material to industry? The material should be cheaper. If we use palladium and CNT, that is much expensive. But if we just use AZ31 with the carbon black, that is very cheap. Yeah. So when we commercialized, we use very much cheaper materials, but it still can reach very high storage capacity, 7.79. Oh, 6.79. So that is about, we already studied such a storage material for more than 10 years. But just 2 years ago, I found our capacity, our performance is very, very excellent. Why did I not apply the patent? So just 2 years ago, I filed a patent. But before my patent approved, one company want me and then want to collaborate with me because they found this patent is very very powerful that can be commercialized. So after they signed agreement with me, I got the patent. But this is Taiwanese patent. Now we apply many countries' patents. We also, our patent also awarded Silver Medal Award in Taiwan Innotech Expo Invention Competition last year. And what's our goal? Our goal is the SDG. And the hydrogen can in the sustainability. And our action is to support hydrogen technology. solid state hydrogen energy research center founded. Yeah. And then we signed a MOU. Yeah. Then yeah. We licensing licensing one patent. Oh, okay. We licensing one patent with $0.8 million. One patent. Yeah. The patent what I show you. Yeah. License 0.8 million. And then the company giving one grant for the industrial collaboration. One project, $1 million. Now we're still working on it. We commercialize our technology. We signed the MOU between ATW Technology Company, 2024, September 3rd. And in our research center, not only me, there are 12 or 13 professors working together in our research center. We divide them into 4 groups. No, 6 groups. Hydrogen production division. Yeah, hydrogen production. And there are some Indian professors. Yeah, 3 Indian professors in our research center. Also, we have the hydrogen storage division. Yeah, professor from National Taiwan Universities, and also my professor from Taiwan Tech. He's my former PhD student. Now he's an assistant professor in our lab, in our university. Also storage, some fuel cell division, professors from other universities, and sensor division from other 2 universities, and also material recycling division, a professor from Taiwan Tech. And in our research center, we have the project manager, and also 4 PhD students and 4 master students working in this project. So, our storage stack working flow is that first we make the materials. We synthesize the materials. And then we store the materials into our storage stack. And then full charge the storage stack, and we connect it to the fuel cells to produce the electricity. That is our hydrogen storage tank. Now we are making the very big storage tank, which can contain about 40 kilograms of hydrogen. 40 kilograms of hydrogen. But actually, this tank is not so big, just about 1 meter, 80 centimeter, and 1.8 centimeter, 1.8 meter height, and then diameter about 2 meters. So we can store 40 kilograms of hydrogen. But our materials weight about 660 kilograms. So we have a small storage stack already produced. It just can store about 0.6 kilograms. It's a small one. Our prototype of the small stack. This is a storage tank. Yeah, we have first generation, second generation, now already third generation. Yeah. Okay, so our ATW solid state hydrogen energy research center stand in the middle of the stream. From upstream, yeah, the hydrogen production from the renewable energy or from the steam, from many methods, yeah, and we can store the hydrogen, and then we provide the hydrogen for fuel cell, and then application to the mobility or industrial electricity usage. Also, we can have the energy storage, yeah, energy storage from the hydrogen storage. Okay. In conclusion, over 20 years of experience in magnesium composite material, from my main research, and then about 12 years ago, I shipped my application of my research to the hydrogen storage, yeah, which is studied from Weizmann Institute of Science, Israel. And then continued steadfastly visiting industry in companies. Almost every week, I went to industry, I went to company to discuss with them what's the problem in your company and what the new product you want to invent, you want to invest. So almost every week I went to company. Taiwan, there are a lot of companies, energy company, mechanical company, chemical company, yeah. So continued steadfastly, week by week, day by day. Yeah. I want to commercialize my research, yeah, to the for the industry. Yeah. Also, finally, we found that AG31 magnesium alloy with the carbonate electrodes, especially the carbon black. Yeah. And accompanied with the ECAD, HEBA, we can reach the capacity of 6.15%. Yeah. And then the storage stack prototyping was accomplished. So from this year, probably third quarter or fourth quarter of this year, there will be the mass production of our storage stack in Taiwan. We have many publications, yeah, also many patents related to the magnesium storage. And actually, we received some grant from our country, from our government, yeah, most, Ministry of Science and Technology, and also many grant from industry, yeah, ATW and other companies. Yeah. Yeah, there are some news in Taiwan. They introduced our research center, our lab. So, yeah, thank you very much for your attention. So there are many co-workers in our lab. Yeah. They were good.
All right. Thank you for Professor Huang's impressive presentation. So, question time, please. Anyone have any questions?
So, we know that for hydrogen storage, the temperature should be quite low. I mean, so much low, like more than negative 200 degrees. So, doesn't it make liquid hydrogen expensive and difficult for commercialize as well?
Yeah. So it's very expensive. You need to liquidize the hydrogen. Yeah, it's the energy consumptive. So the cost is very high. For 1 kilogram, probably you need to cost 1,000 US dollar to store, liquidize. So it's so expensive, huh? But in our method, yeah, 1 kilogram, the material it just cost $20. Yeah, $1,000 compared to $20. If you are boss of the company, which method you want to use? Yeah, it liquidize so expensive. Yeah.
So the energy cost of liquefaction is about 1/3 of the calorific value of the hydrogen. What's the energy cost of your process? How much energy do you have to put in and then take out for the storage?
Actually, we have calculated the cost. Yeah. For example, the hydrogen now is pure hydrogen is expensive, about $10 1 kilogram, or $20. Yeah. And in our commercialization, we use the gray hydrogen, even green hydrogen. But we can get some green hydrogen for almost free. We use the biomass to produce the hydrogen. So in the typical cost of the hydrogen production and hydrogen storage, also the electricity production, the totally will cost a lot. If 1 kilowatt hour electricity want to produce cost more than $20 or $30. But in between, half of the cost is allocated in the storage and transportation, about 50. Yeah, probably $15 or $20 for 1 kilo, but for one kilowatt hour. So what we are doing now, to reduce the price of storage and transportation. So the half price will be gone. So yeah. So we have calculated all the cost, yeah, and by our prototype, yeah, everything. And the company here, wow, is very managed. If we use the metal hydride storage. Yeah. Sorry, can I answer your question?
Or not
No.
quite. I was asked actually after what portion of the energy that you store. So if you store 1 kilowatt hour of energy in the hydrogen, how much energy do you lose in the process of the storage and the retrieval? So if you have a kilowatt hour of hydrogen gas and you liquefy it, then 1/3 of that is lost in the liquefaction process. Yeah, but you can get it all, you can use all the rest. So what portion of the energy in the hydrogen would you use for the storage process? And this is store and retrieve.
What's the portion?
Yeah, what portion of energy have you lost from your hydrogen through having to store it?
Actually, we did not lose the energy.
Well, the hydrogen has the energy, but you've put in extra energy to do the process. How much is that?
You know, now we met the difficulty you mentioned, that is energy. In our absorption, we need a lot of energy.
Yeah.
Yeah, 300 degrees Celsius. And now we found the best solution that we can work with the SOFC, solid oxide fuel cell. Solid oxide fuel cell, when they're working, they produce very high temperature, above 600 degrees Celsius or 900 degrees Celsius. They produce a lot of heat. And then we absorb such a heat as our energy in our absorption and desorption. So just recently we got a best solution because we need a lot of energy to store and then absorb the energy, then absorb the hydrogen. Yeah. So we studied with the company for more than 1 year, but recently we got a solution, and our boss is very pleased, very happy. Yeah. So they invest more. Invest more millions US dollar. Yeah. They saw the future. Thank you for your question.
We have more questions today? Okay, probably my last question from the normal one. So, I'm not an expert in energy storage, but could you briefly talk about the safety and cost like this issue? So, let's say we know maybe hydrogen will cause explosion, something like that. How is that safety level?
Oh, yeah.
Correct. The research.
It's very important for safety level. Yeah, because for the pressed tank, it's high pressure. High pressure, if something happens, the exposure will happen. Yeah, high pressure of gas. But in our storage method, we only need 3.5 megapart to compress the hydrogen. So that is very small pressure. So it's very safe. But the dangerous situation is when we absorb and desorb the hydrogen. That we need a high temperature, 350. But when we are absorb and desorb, we all do it in the vacuum environment. Also, no water, no oxygen, no any airs. So it's very high tech to absorb and desorb the gas, the hydrogen. Yeah. So in the transportation, all are in ambient temperature and pressure transportation. So it's quite safe. So there's no issue of safety during the transportation. But if you use a precious tank, well, it's very dangerous, like a bomb. Exposure anytime. But in our storage technique, everything is in normal temperature and normal pressure. But in our production, it's very sometimes dangerous. Yeah, because we make the powder, magnesium powder, it's more easy to be explode, and also with oxide. So we do everything is like in the yellow light room, or no water, no oxygen, no atmosphere environment to make the powder. So it's very
Yeah. Alright. So probably probably the end of today's seminar. So let's give just warm welcome to Professor Huang again. That's the end of our seminar. Okay. Thank you.